Hello, everyone. Today we are going to be doing some daily research paper reading. This is a goal that I've set myself where I want to make videos every day, reading new papers, specifically in the robotics field for robot learning. And today, the paper that I wanted to look at is. Oh, by the way, is my mic okay? Yes, okay, it is good. Today, the paper I wanted to look at is reinforcement learning with action chunking. And I've not read this paper in depth, so we're going to be reading it together. It's not like I'm just recording myself like going through this paper and learning it. Um, so, and I guess the reason for that is because if you look at, I saw Karpathy. One of Karpathy's tweet was, to become an expert on something, you have to teach and summarize everything you learn in your own words. And so this is what I'm trying to do. Also, the reason I'm not talking super loudly is because it is kind of early, 8:15, and my roommate is sleeping. But anyways, so we present Q chunking, a simple yet effective method recipe for improving RL, right? So I guess it builds on top of Q learning, and I guess we first should understand um, the Q learning. What is the update for Q learning, right? Um, and so I'm going to do that in a bit. I guess like we should go here and go through spinning up and read this. So we understand what a policy is. We understand what a deterministic policy is. A policy will, given a state, output an action. If it's deterministic, then given the same state, will always give the same action. If it's stochastic, then you sample from it. And then deterministic. Okay. I see. Yeah, okay, that makes sense. It's like discrete tokens, and then you output the log. You learn the log likelihood. Yeah, this log likelihood has always been like, It's the log probability. Okay. So the sum of these probabilities must sum to 1, and you essentially take the log of those probabilities. And so what it's going to do is it's going to make the smaller numbers smaller, make the bigger numbers bigger. Alright, that's softmax, sorry. Oh. E to the 1 is E. That's E to the 0.15. I guess it's going to amplify the differences. Yeah, that's right. Alright, so when we maximize in behavior cloning, what we're trying to do is maximize the log likelihood. Okay. Like, let's go to my iPad. This equation, it makes a lot more sense now, I guess, right? So in behavior cloning, right, what we have is like a state and an action sampled from a data set, right? These are expert demonstrations. And our objective is going to be to maximize the log likelihood of phi of action given, right? We're going to try to maximize this. Now, how do you actually maximize this? This doesn't mean anything, right? So it depends on how your model is implemented, right? So if it's a categorical policy, what you're simply trying to do is maximize, and this, by the way, behavior cloning, right? What you're trying to do here, you can expand this out. If it's a categorical policy, what you're trying to do is simply, given if P, what this, oh, by the way, why does this look so bad? Okay, it's because it just happened to be exactly like this. Right, this last layer is exactly P of theta S. And so your objective is simply maximizing the log probability in the case of categorical. In the case of like diagonal Gaussian, what you're learning is like, instead of learning the probabilities of each action, instead of them being categorical, right? Well, first of all, this has the requirement that these actions are discrete, right, in categorical policies. But especially like in robotics, you're working with like in continuous space, right? So you can't just like, predict these discrete tokens of what possible actions you have. So each action is continuous. So if each action is continuous, what can you do? Well, maybe what you can do is for each dimension of the action, right? So you have like a1, a2, an. What you do for each of these actions is that you can sample. You want to sample some number, some continuous number, right? And so we can make use of a Gaussian distribution, right? And what we can do is we don't know the parameters of this Gaussian, but we can have a neural net, because a Gaussian is just parameterized by mu and sigma, right? Where mu is the mean and sigma is the variance. And given these two numbers, you know how to sample from a Gaussian, right? And you do that for each of these dimensions. And so I think that's what a diagonal Gaussian is. And so a diagonal Gaussian is a special case where the covariance matrix only has entries on the diagonal, and which basically means that each variable is independent of each other. Right, there's another, it's called a Gaussian process. Or it's called, yeah, I have it here. You look at this. This is a visual, a very good visual. So this is a kernel. You see, if you have a length of 0.01, right, a variance of 1, right, so this is a variance of 1. This is like how this controls how correlated each variable is to each other. You see how if they're not correlated at all, you just end up with this one diagonal. But as you become correlated, you get this. Okay. And then once you do that, at inference time, you say you have these numbers. The way you sample it is like they have this equation. I mean this equation is just like I guess if you know how to sample z from n1, then the way you get that is mu plus z times sigma, right? And that's basically it. This is very basic. I don't know why they wrote that, but I guess sure. And then this is more interesting is here. Okay, so if we have a diagonal Gaussian policy, the log likelihood for Gaussian mean is given by this, right? Because essentially what this is just, if we go back to Gaussian distribution, it's this equation. And when we want to do maximum likelihood estimation, oh, it's essentially this equation, right? Yeah. The definition log. What is the definition of likelihood? Yeah. So you have the probability density function. Okay. Yeah, it's just the product of this, right? And if you expand it out, the likelihood of observing mu and sigma squared for given mu and sigma is given by this. And this likelihood, okay, likelihood, all it means is the probability of seeing your data given some parameters that you have, right? So, for example, you could ask, what is the likelihood that you see, you have some data, what is the likelihood that this data has a mean of mu and variance of sigma squared, right? For some mu's, it could be 5, it could be 10, okay? But we can just call it mu and sigma squared, right? So what is the probability that given your data, you have mu and sigma squared? And so the definition, I guess, is pi event, I guess, right? Oh, and this got fricked up. I just messed it up. Alright, so you have mu. The definition is just the product of seeing your data given data. Where data is the parameters. Right, so the likelihood of x given data, so for Gaussian, it would be the probability, it's essentially, if it's a distribution, so you're looking at your probability density function, which is f of x given data, which is equal to Gaussian, which is equal to 1 over, and then this data has mu and sigma squared. So the probability of 1 over 2 pi e minus 1 over 2 x minus mu over sigma squared, right? And it's going to be, you generally have like multiple samples, right? But I guess if you only have one sample, it doesn't matter. So this derivation, oh, wrong screen. I guess it's a more generic term, right? How do we pull out a log here? I guess because you usually have multiple data points. When you have multiple data points, then it's like yeah, yi. So you have multiple data points, and you want to maximize this probability density function, or it's maximized when the derivative is 0. Okay. And so yeah, we're just trying to maximize the likelihood. yeah, it's just that, and then the log likelihood is essentially you take the log of your likelihood. Like it's not that complicated, and but interestingly, this is just likelihood, right? So this formula is just what is the likelihood of it's just a product of your right. How do I not know what a PDF is? It's the area under the curve. It's the density. It essentially is a function such that the integral between a, b, f of x dx is equal to the probability, to the sum of the probabilities from a to b, right? Yeah. Yeah, that's what I was trying to say. Yeah, I don't like the fact we use y here. I'm gonna change it to x. You want to maximize the likelihood because you want to maximize the probability thing. You want your parameters to be such that when you sample from a distribution, it represents your target data distribution, right? And so what we're doing, once again, to reiterate this log likelihood, right? What is our objective when we're doing behavior cloning, right? We have some probability, like forget the log for a second, right? We have some policy that outputs a given some state, and it's parameterized by some data, right? We have some action and state that's sampled from D, right? And these two should be matching, right? So we want Pive's data to be sort of equal to D, the target data distribution, right? And so that is essentially what we're doing. We just want to maximize this. And we just add a log in front of it for training stability. Okay, the Bellman equation. Oh. Yeah, okay. We know this. This is the advantage. Is how much better an action is. We're randomly selecting according to like given some policy. What's the average? I think actually I like this better because as sampled from P, and this is the expanded version of this. I think I should write the non-expanded version. Alright, but this is in a discrete setting, right? There's no wing here. Okay. Hmm. Yeah, I guess expanding. That's valued. Yeah, I think um, if you don't know how to write the Bellman backup, then you're a noob. Which I am. Do people still? Is this still maintained? Oh my god, it's been 5 years. Can you explain Q-learning? Oh, okay. Wait, were you supposed to read this paper? Alright, I need to continue this tomorrow. It's been an hour. Alright.